optimization. I'm your host, Dr. D. Okay, here we go. Now, there are certain sections in the calculus course that just the name makes you feel something. Like if you remember the term related rates, you feel something there. Optimization is kind of like that too. Optimization, first, it makes you feel a little uneasy, a little bit like, oh no, how are we going to do this? And then you start getting into it and it starts feeling better, and pretty soon you're feeling kind of like... Okay, I'm starting to get this thing now. Yeah, I actually know what I'm doing. I'll sleep all day, I'm alive. It's kind of like that. Okay, so here we go. We're just going to go right through the examples in the book. If you take a look at the first page of the section on page 331, it's got steps in solving optimization problems. Really, it's just like solving word problems, just that 5-step process that I gave you in Algebra 2. The most important beginning is draw the picture, define the variables, write the equation, and then go to town. So, check out example 1. A farmer has 2,400 feet of fence. Oops, I messed up already. 2,400 feet of fence, not area of 2,400 feet. Okay, so we have 2,400 feet of fence, and we've got a river on one side of it. So the perimeter is set at 2,400 feet. And the area, we don't know. Now notice pictures in the book. If we make a long, narrow fence, then we'll use up our 2,400 feet of fence and we'll have a certain area. If we make a tall, skinny fence, same thing. We'll use 100 or 1,000 feet on both sides and 400 foot across. That'll give us our 2,400 feet, and it'll give us a certain area. We want the biggest area that we can get with that 2,400 feet of fence. Now, with the river on the bottom side, we don't count that side, so we really only count the 3 sides. So that's why perimeter is 2x plus y. Now, basically, we just defined our variables by drawing the picture. Here's x, here's y, and clearly the area of a rectangle is base times height, or I should say height times base. So it's x times y. All right, now maximize the area that we have here. Well, the maximum area is going to be where the derivative of area equals 0. But see, we can't do the derivative of area if we have 2 variables. We only want 1 variable. So what we have to do is we have to choose either x or y, and if we choose x, then we want to solve for y in terms of x. So let's do that then. All right, so perimeter is 2x plus y. That means 2,400 feet equals 2x plus y. So what's y equal? It equals 2,400 minus 2x. Now, what I can do is I can plug in my y value in terms of x. So my equation then is area equals x times y. So now I have area in terms of nothing but x. So if I want to get the maximum area, then all I do is take the derivative of this thing. Now, I don't want to take the derivative of a product, so I'd rather distribute the x and just say, okay, area equals 2400x minus 2x squared. Now, the derivative of this is going to be 2400 minus 4x. Now remember, we want the maximum area, so we want the maximum of this function. That means we set the derivative equal to 0, and we solve for x. So 4x equals 2400, and x equals 600. All right, so if x is 600, then that means we've got 600 plus 600 is 1200. That means to make the entire perimeter of the 2400 feet, we have to have y equal to 1200. So we go, yeah, let's just write like this. 600 feet here, 1200 feet here. That gives us our 2400 feet perimeter, and it gives us 600 by 1200, which is 720,000 square feet. Is that the maximum, though? See, because remember, when we take the derivative of a function, set it equal to 0, that could be a maximum, it could be a minimum, or it could be a point of inflection. Now, clearly this is a quadratic, and notice the equation 2400x minus 2x squared. That's a parabola that opens downward. So there's no way it's a minimum or a point of inflection. We know for a fact it's got to be a maximum. Now, the other way to prove that this is a maximum and not a minimum is to take the second derivative. So I go oh no, it's in red. How embarrassing. A double prime equals 0 minus 4. Now, what does that mean? Well, the second derivative is negative. That means we've got concave down. That means it has to be a max. Now, you can determine whether your quantity is a max, a min, or a point of inflection several ways. One way, knowing the function, it's a parabola opening downward, that tells you it's a max. Second way is I could do the first derivative test. So I take a value to the left of x equals 60, and I see if that's positive or negative. So if x is less than 60, then a prime is going to be positive. If x is greater than 60, a prime is going to be negative. So if I have positive slope to the left and negative slope to the right, then I have a maximum. Now, one other way of doing this, let's say you don't want to plug into the first derivative, you don't want to do the second derivative test. There's another way that I basically call common sense. You look at the fencing and you say, okay, if 600 by 1200 is a max, then no other dimensions could be greater than that. And if there are any other dimensions that are greater than that, then that must make this a min. So, can we think of other dimensions that are less than 720,000? Well, yeah, look at in the book, you've got the 100 by 2200, which gives you 220,000. So clearly 720,000 is greater than that. That means 720,000 if it's a min or a max, has to be a max. That's it, game over. Okay, so cruising onward. Let's see, example 2. Now notice, I'm doing the exact same thing. What did I do first with this fence problem? Drew the picture, labeled the parameters, identified my equations, then made an equation with a function of one variable. That's it. Okay, we're going to do the same thing. We've got a can, and this can holds 1 liter of oil. And what we want is the dimensions of the can that's going to hold our 1 liter of oil, that's going to minimize the surface area of the can. Basically, we're trying to make this can as cheaply as possible. Now, let's just say we make it super tall. Like we make H really big. Let's make H like 3 foot tall. And then the radius would be almost like an inch or so. That, to get 1 liter, it would be tall and thin. Now that's going to take a lot of material to construct it that tall. And likewise, if we make H super small, and that would make the radius have to be super big, so it would be like a giant coin, you know, like real thin and wide, a huge amount of material. So there's some medium height and radius that's going to give us a 1 liter volume that's going to minimize the area. Well, we're talking volume and area. So volume of a cylinder is pi r squared h. And area of a cylinder is going to be the area of the top plus the area of the bottom, which is pi r squared times 2. Plus the area of the sides. Now if you were to unravel the sides, then you would have 2 pi r is the circumference. So that's basically the width of the rectangle times the height. So 2 pi r h is the surface area of the side. All right, now, once again, we're trying to minimize area, but we have our area in terms of both radius and height. So we need to get height in terms of radius in order to have one variable. Remember, we're looking for area as a function of one variable. Well, so we know that volume is pi r squared h, and that equals 1. Okay, so, wait a minute. You know, what we're going to have to do is we need to make sure our units are correct. And that's part of the problem with the metric system. 1 liter is 1,000 cubic centimeters. Okay, so that's actually the volume we want, because we want to talk about radius and height in terms of centimeters. So that means pi r squared h equals 1,000, and that means h in terms of r, all we have to do is get h alone. Okay, so we say h equals 1,000 over pi r squared. Okay, so cruising on back here, we say then the area equals 2 pi r squared plus 2 pi r h. Now, we want to minimize area, that means we need the derivative of area and set that equal to 0. Okay, let's clean this up a little bit. So we've got area equals 2 pi r squared plus, now something is going to happen here that I hardly ever like to do in a restaurant, and that is cancel the pi. See, we cancel pi, get it, see that? Okay, so then we have 2 times 1,000 is 2,000. Now, r over r squared is just going to be r. All right, so 2,000 over r plus 2 pi r squared. Or the other way we would write this is, let's just write like this, 2 pi r squared plus 2,000 r to the negative 1. Okay, now let's take the derivative of area with respect to radius, with respect to one variable. All right, remember, 2 pi, that's just a constant. So we bring the 2 down and we have 4 pi r. And then this is going to be minus 2,000 r to the negative 2. Now, we want to set this equal to 0. So we need to clean this up. So it's going to be 4 pi r minus 2,000 over r squared. And really, to make this easier, let's get a common denominator here. So we're going to say this is going to be, multiply this by r squared. So it's 4 pi r cubed minus 2,000 all over r squared. Now, the thing that makes it nice, if I want a fraction equal to 0, all I do is set the top equal to 0. So I've got 4 pi r cubed equals 2,000. And I'm trying to get r by itself, so divide by 4, so you have 500. So r is going to be the cube root of 500 over pi. And let's see. They give us a decimal equivalent here. No, they just left it like that. All right, so we'll just leave it like that. So if r is the, not the square root, but the cube root of 500 over pi, then what's h going to be? Well, h equals 1,000 over pi r squared. So we can get h, and h turns out to be the 2 cube root of 500 over pi. Basically what we would do if we wanted to verify that is we would plug in the cube root of 500 over pi in for r. So you have 1,000 over pi times cube root of 500 over pi squared, and then you simplify that and you get 2 cube root of 500 over pi. Now, notice what we're saying then is the the minimum area is when the height is twice the radius. That's going to be for any cylinder. When the height is exactly twice the radius, then you're going to get the minimum surface area of the walls for the volume, for any given volume. Now, how do we know, once again, that this is the minimum area? Well, we could take the second derivative, which would be kind of a nightmare because we end up with, oh, I guess no, it wouldn't be. If we take the second derivative right here, that ends up being easier. So let's check that out. If we take the second derivative, then we're taking the derivative right here. So that's going to be 4 pi minus, now, it's actually not going to be minus because we bring the negative 2 down in front, and that means it's going to be plus a 4,000 r to the negative 3. So that means a double prime equals 4 pi plus 4,000 over r cubed. Now the thing that you see here is a double prime is always positive because there's no way radius could be negative. So a double prime is always positive. What does that mean? That means we have concave up. Concave up means that the critical point is a min, which is what we were hoping for, because we want to minimize the area. Now, the other way of verifying this is to say, if I use any other dimensions, will the amount of material be greater? And the answer is yes. So, like I said, if you say, let's make radius really huge, then I'm using more material, which means this critical point has to be a minimum. That's it, game over. Okay. Cruising onward. Example 3. We've got a parabola that's y squared equals 2x. And we've got a point that's 1, 4. Okay, so here's our y squared equals 2x. It's a parabola that opens to the right. And now we have a point at 1, 4. And what we're trying to do is minimize the distance from the point to the parabola. Now, if I were to eyeball it, I would say the closest distance would be like right down like that. It looks to me like the point on the parabola we're looking for is 2, 2. Now, this is going to help when we get the answer to check it to make sure it's reasonable. Because if we got the answer and we said, oh, it's 6, 5 or what, 6 whatever. Oh yeah, I could figure that out. But yeah, if it was something out here, then it's like, no way, that's not nearly as short as this. Okay, so minimize the distance. Well, what we're going to do is we're going to call this point xy. That's the point on the parabola that's closest to the point here. And we'll call this distance d. Now, what is the distance? Well, we just use our distance formula. This point is, 1, 4, not 4, 1. All right, so the distance is going to equal the square root of the x minus the x plus the y minus the y. There's my distance formula. Now, if I want to minimize distance, then I have to take the derivative of this mess and set it equal to 0. Thing is, I don't like that idea. That's got like the chain rule and it's got all sorts of messiness in it. So what I would rather do is I would rather say capital D equals x minus 1 quantity squared plus y minus 4 quantity squared. Now what I actually want to do is I want to minimize capital D. Now see, let's get the logic here. I could minimize the distance, but instead what I want to do is I want to just take what's under the radical and minimize that, because if I minimize what's under the radical, then I'm actually minimizing the distance. So to make it simpler on ourselves, we just say, I don't really care what the derivative of this radical is. I care about minimizing what's under it, which will in turn minimize it. So I just want to minimize this term without the radical. Okay, now, the other thing we've been talking about all along is we have to have a function in terms of one variable. So, let's see, you could make x in terms of y, or you can make y in terms of x. So if I were to make y in terms of x, then I would say y equals the square root of 2x. And if I was going to make x in terms of y, then I would say x equals y squared over 2. Now, I like the y squared over 2 a little bit better, because then I don't have a radical in here for the y. So let's do that. So we say d equals x minus 1 quantity squared plus, oops, I went the other way. Cut, take 2. D equals x minus 1 quantity squared plus y minus 4 quantity squared. Okay, let's take let's square both of these, and it's going to make it easier to take the derivative. So d is going to equal, okay, a squared, which is going to be y to the 4th over 4, minus 2ab, which is going to be 2 times y squared over 2, which just makes y squared, times 1, plus 1. Now, plus y squared minus 8y plus 16. Okay, now notice the y squareds cancel, and so I have d equals 1/4 y squared minus 8y plus 17. So that makes d prime equal to 2 times a 4th is 1/2 y minus 8. Now I set that equal to 0, and it turns out then that y equals 16. Now, see, this is exactly what we were talking about. Something has gone awry. What the heck happened? Yeah, y should equal 2, and it doesn't. Why doesn't it? Oh, how come you guys didn't tell me about that? Yeah, let's just get rid of everything here. when I simplified d, I just threw away the d to the fourth. So it's 1/4 y to the fourth. Now the y squareds are still gone, minus 8y plus 17. So d prime equals 4 times 1/4, which is 1y cubed minus 8. Now, we set that equal to 0. That's a little happier. Now, y cubed equals 8, which means y equals 2. Now, if y equals 2, then you square your 2, 2x equals 4, and that means x equals 2. Now, so we found out that the point we're looking for is in fact 2, 2, like we thought from the beginning. Now, let's see, is this a minimum distance or a maximum distance? Well, that's kind of a silly question, but let's go through the exercise. If I take the second derivative, then what happens? Well, the second derivative is going to equal 3y squared, and at y equals 2, the second derivative is going to equal 12, which is positive. Well, if the second derivative is positive, that means it's concave up, and that means the critical point is a minimum. I said that was silly to even go through that exercise, even though that was pretty easy. The easier way of saying it is, this is either a minimum or a maximum distance. Well, is any other point on the parabola going to be further away from this 0.14 than this? Of course, any point will be. Like if I take a point out here, it's going to be way more. So that means that has to be a minimum rather than a maximum. So the closest point to 1,4 on the parabola is 2, 2. That's it, game over. Okay. One more problem, and then I'm turning you loose on the homework. All right, this time we have a person that's on one side of a stream at point A, and he wants to get to point B, which is across the stream and also downstream from it. Now, apparently this stream is moving so slowly that the current has no effect. So it's almost like a lake that he's swimming, a rectangular shaped lake that he's swimming across. And the distance across is 3 kilometers. So clearly this body of water is in France. Okay, so he wants to get from point A to point B. Now, he can move on the water at 6 kilometers per hour. He can move on the land at 8 kilometers per hour. So what that means is he's got a couple of choices here, actually 3 choices. He could row across or swim across. I don't know what he's doing. Yeah, he's probably rowing. Yeah, he's in a boat. He's not swimming. Okay, so he could row across from A to C and minimize the distance across the water because he's slower on the water. And then he maximizes the distance on the land because he's faster on the land. So first choice, go from A to C and then C to B. Second choice, he could say, well, I want to go the shortest distance no matter what the speed I go. So I'm just going to go straight from A to B. So that's maximum water travel, but minimum distance. Or the third option would be to row across to some intermediate point D and then walk the rest of the way down from D to B. Now, we want to explore all 3 options. So if we, first of all, we're trying to minimize time. That means we want a function of time with respect to distance. So I know that rate times time equals distance, which tells me that time equals distance divided by rate. Okay, so if I say, let's make the distance from C to D is going to be x, and the distance from D to B is going to be the rest of the way to 8, which we'll call 8 minus x. So no matter what x is, if I add it to 8 minus x, I end up with a total of 8. Okay, so since time equals distance divided by rate, then if we go from A to D to B, then what is the distance from A to D? Well, notice this is 3 kilometers across here. This is x, and so A to D, the distance from A to D is going to be the hypotenuse of that triangle. So that's going to be the square root of x squared plus 9. That's distance from A to D. And while we're at it, we could say the distance from A to B, if we went directly from A to B, well, we've got a 3 and an 8, and so that's going to be 64 plus 9, which is 73. So that's going to be the square root of 73 kilometers for that. And clearly, distance from A to C is 3. Okay, so now what we want to do is we want to say, let's get the time from A to D to B. Now, if x happens to, well, let's say if the best route would be to go from A to C to B, then x will turn out to be 0. And that'll say you just go straight from A to C and then down to B. So the time then is going to be distance divided by rate. So we're going to go from A to D on water. So the time from A to D is going to equal the distance from A to D, which is square root of x squared plus 9, divided by the rate from A to D, which is 6 kilometers per hour. And then the time from D to B is going to equal the distance from D to B divided by the rate from D to B. Okay, so we have the time from A to D and the time from D to B. So our total time is going to equal square root of x squared plus 9 over 6 plus 8 minus x over 8. And now, remember, we're trying to minimize time, so we take the derivative of time with respect to x. So t prime then, let's see. Yeah, let's just change this up a little bit. So it's 1/6 times x squared plus 9 to the 1/2 plus, now let's change this into 8 over 8 minus x over 8. So plus 1 minus 1/8 x. 8 over 8 is 1, and x over 8 is 1/8 x. So now we're going to take the derivative of of t with respect to x. So t prime is going to equal 1/2 times 1/6, which is 1/12 times x squared plus 9 to the negative 1/2. And then don't forget we've got the chain rule. Okay, so the derivative of the inside is 2x. Now, the derivative of 1 is 0. The derivative of the minus 1/8 x is just 1/8. So we can... Okay. So, let's clean this up a little bit. So, the 2x times 1/12 is going to be x over 6. So, x over 6, and then this x squared plus 9 is the square root on the bottom, and then minus 1/8. Now, this is t prime. We want to set t prime equal to 0. So now we move this over here and we say x over, let's see, let's make some more room. Yeah, we'll just have to squeeze it in here. All right, so that means x over 6 squared of x squared plus 9 equals 1/8. Now, that means 8x is going to equal 6 squared of x squared plus 9. And now if I square both sides, then I have, oh, you know what, before we square both sides, let's get rid of the, divide both sides by 2. So that means we've got 4x equals 3 squared of x squared plus 9. Now we'll square both sides. So that means I've got 16x squared equals 9 times x squared plus 9. 16x squared equals 9 times x squared plus 9. All right, so that means we've got 16x squared minus 9x squared is 7x squared equals 81 divided by 16. Yeah. Did I do that right? Let's see. Yeah, that's 81 divided by 16. And now if I, so that means x squared equals 81 16ths times 1/7. That means x is going to equal 9/4 times 1 over the square root of 7. So, so at this point, it's time to turn that into a decimal. If x okay, let's do one other thing. Yeah, let's turn that into a decimal. So 9/4 Nah, I screwed something up again. All right, take 2. What did we do here? I tried to take a shortcut here. Let's just go 16x squared equals 9x squared plus 81. Yeah, there is no 7 there. So now, Yes, 7x squared equals 81. Yeah, 7x squared equals 81, and that means x squared equals 81 over 7, which means x equals 9 over the square root of 7. That's better. So if x is 9 over the square root of 7, then that turns out to be approximately, oh, we don't care. We're going to plug it in first. All right, so 9 over the square root of 7 is the x value, but we want the time that that's going to take. So what we're going to do is plug in 9 over the square root of 7 in for the time here, and get a decimal approximation. So you know what, I'm going to do that with my calculator. So what we're going to do is just go